The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we're going to talk about the dynamics of running and ask questions as freely as possible. And also, if my handwriting's bad, let me know. It generally is. So this is actually a really fun lecture. We have a lot of cool videos. I don't know if you've seen Raybert's hoppers and stuff before, but we have some cool models and some cool analysis too. So hopefully you'll be as excited as I am to participate in this learning experience. So here we go. So the basic model we're going to look at today, and several different sort of versions of this, is the slip model. This is the spring-loaded inverted pendulum. It's sort of like the running version of the rimless wheel or compass gate. It's pretty simple. You just have a mass at the end of a pendulum. You have a spring here, a spring constant K. The spring is a rest length, R naught, and I said spring constant. And so then the coordinates then are this length R, and the angle theta from the upright. Okay. So what we're going to want to look at here is not just this model, but also in the same way we had for the rimless wheel, as you remember, is a 1D iterated map. So you probably remember that for the compass gate. That lets you look at the stability of it, and there's all these interesting dynamics that are captured by that simple system. So we're going to look at the 1D iterated map, and the other thing I'm going to try to convince you is that this is a biologically plausible system. So if you look at the rimless wheel, it sort of feels like something that's walking. Compass gate even more so, and then you knees. These things all sort of just intuitively you can believe that they're, well, that's probably going to be bad. That you could believe that they're walking systems. But this one maybe doesn't seem to you immediately like a running system. Maybe it seems like a jumping system or bouncing system or something. But actually, it actually is a pretty good model for running systems. So the two things that we're going to have to go through: how to get a 1D iterated map. That maybe is a bit surprising for you, because if you look at this, the full state space of this inverted pendulum right now, it has states of R theta, R dot, theta dot. Now that's 4 parameters. So when you remember when you slice through and you pick a surface of section, you can cut it down by 1. So for the rimless wheel, maybe you have theta, theta dot. You cut out theta dot, and you're in pretty good shape. Here we have 4, but we're actually going to show that we can actually get this down to a 1D system and actually look at the iterated map for this. So that's kind of cool. And the other thing is that also this system bounces and takes off. So actually we need 2 coordinate systems. One is this R theta, R dot, theta dot. And then when it's in flight, we're going to have X, Y, X dot, Y dot. All right? And both of these are 4D, so we have to deal with that either way. But first, the convincing part. So the justification here comes from a field called comparative biomechanics. Now this is a pretty cool field. They look at all sorts of different systems and try to sort of figure out these commonalities in the kinematics, the dynamics, or certain properties, and figure out sort of what are the fundamental, common features of these different biological systems. So this running model, actually, you can look at it in the context of things from cockroaches, which are on the order of a gram in mass. Horses, which are on the order of, well, some of them at least are 135 kilograms. It's not that heavy release. You could imagine maybe heavier horses. Crabs, now, you can think about the kinematics of these systems and just how wildly different they are. Cockroaches, 6-leg, bouncing all around, follows a tripod gait. Horses, quadrupeds. Crabs, actually, they run sideways with 8 legs. Well, this is different information, so I won't put it there. But crabs actually will run sideways using their 8 legs. It's actually pretty cool. I don't know if you've seen it. But, and then humans, which maybe is the one that we most, well, that's probably unfairly biocentric. So there's humans. And all of these, despite the very different kinematics, despite, what is this, 5 orders of magnitude in mass, they all have incredible dynamic similarity. Let's hope I'm not getting graded on spelling, because I'm pretty sure that's way off. And so if you look at them in the right way, you can actually see that all of these systems, cockroaches, horses, crabs, camels, cats, bunny rabbits, all these things actually look very similar. And so Bob Full, some of you may know Bob Full, I think at Berkeley. He looks at a lot of these things, especially the cockroach work. He has a lot of cool work on cockroaches. And he also has this paper which, let's see if I can, what page is this on? Sorry, here, there we go. Is that clear up there? Ooh, sorry. So here, you can look at the, let me dim the lights a bit. If you look at the plot on the left, this is speed and the stride length. So if you plot speed and stride length, here they've got gerbils, dogs, and camels, but you can do this for a very wide variety of systems. You can see that they're sort of all bounced over the place. You don't have, I mean, they're all behaving very differently. That's not necessarily the right way to look at them if you want to sort of see what is fundamentally similar between them. If you look at the right, this is the Froude number. In this case, you can see it's just the ratio, well, it's 2 times the ratio of kinetic energy to potential energy. So it's just this non-dimensional quantity. If you plot this and you look at the relative stride length, which is, you can see they all sort of collapse very tightly on this line. And so that's actually sort of like, that's impressive agreement. You see that these are, camels, dogs, and gerbils are all sort of, look very similar when you look at them in this sort of non-dimensional way. So all these systems, orders of magnitude, again, of difference in masses, stride lengths too probably, all look very similar when you compare them in the right framework. And that's sort of what comparative biomechanics tries to do, in addition to other things, obviously. But so here's something that's really cool and that connects us back to our slip model. If we look at the next page, you'll see right here. This is the relative spring constant for an individual leg for all different systems, cockroach to kangaroo, 5 orders of magnitude. You can see that they're all pretty similar, right? This is huge spectrum of masses. And yet in the framework of the slip models, spring constant, they all behave pretty similarly, humans, all these things. And so if you look at these systems through this simple model, they all not only look similar to one another, but their dynamics and their center mass direction, everything like that, are pretty well described by this kind of behavior. By that kind of behavior. So hopefully that'll be, somewhat compelling argument that this model is representative of actual running behavior, not just something that comes out of nowhere. And a lot of work was done on this in the 80s and 90s on trying to sort of study this model and connect it to animals and that sort of stuff. And I don't know if you've seen Raybert's work, but he has robots that are very similar to this sort of slip model that run and jump and actually are from the 80s and such like that. Actually are some of the really cool robots, and we'll show you some of those. So he actually didn't even call them slip. He actually made them before slip, and that motivated some of the work on slip models. But I can show you, I'll show you a picture of a robot so you can see the kind of cool stuff they were getting to. I don't know, are many of you familiar with the Leg Lab? They used to be around. Yeah, they had a lot of cool robots. And here, see if I can give you just a little picture. Well, so that's the biped robot. This thing's bouncing, but that's not really the picture I wanted to show you. Here we go. Yeah. So this little robot, you can see that's sort of a tracing its foot. This up here is tracing its center mass, and you see how center mass actually compresses right above the foot. And so that's sort of what you expect here. It lands and it squishes down. And so instead of when you're walking and you sort of vault over this leg, like you think about that rimless wheel, center mass rolls up over its foot. This one, both intuitively in the model, and you can see right here, this robot, which is similar to the model in many ways, is squishing down into its foot. All right? And that actually is one of the ways of looking at the difference between what is running, what is walking. So one of the definitions for running is that you're supposed to have an aerial phase, but not every running animal has an aerial phase. So this is actually, I think, comparative biomechanicians look at this sort of center mass to center of pressure kind of trajectory, because I don't know if you know Groucho Marx. Groucho Marx had this funny run. Maybe I'll do it, so maybe it's different posterity, but sort of like this, that kind of goofy thing where your feet aren't coming up the ground. That doesn't seem natural, but actually some animals do that. There's actually elephants that sort of do that Groucho run. So maybe if you're big enough, it makes sense. But yeah, so you see this is very different from walking, and it's actually quite similar to running, and actually if you look at these animals, it captures a lot of their dynamics. So, yeah, and another important thing is that these kind of robots, which came around in the 80s, were sort of a similar kind of work in robotics, because again, at the same time whenever these sort of slow, careful kind of walking robots, again, here are these robots that are flying through the air. I'll show you some of the videos later, but they did flips and all kinds of crazy stuff. I mean, they were throwing themselves around wildly, which is not what people sort of thought of when they thought of these sort of, legged robots. Yeah. So, and the other thing, this is cool too. If you look at animals, like we're talking about the springs and stuff like that, that's not just sort of some sort of obtuse model that comes out of nowhere. If you look at horses and stuff, well, animals actually are full of springs, like their tendons can store up energy and stuff. And actually, horses have a big tendon that runs through their leg all the way up, I think, behind their hip. And apparently one of the limiting factors in trying to run fast is that you can't pull your leg forward fast enough to get to the next stride. And so what they actually can do is they can preload when they're pushing, and then that tendon actually acts like a spring and actually stores energy and lets them swing forward faster than they would be able to if they just used the motor. And if you look at the oxygen intake of these animals, you can see that they're behaving much more efficiently than you could hope to accomplish if you just had if you were simulating a spring with a bunch of motor with like your muscles acting like a spring, right? So it's actually their physical springs, like actually this tendon in there actually have this actual behavior. So hopefully, maybe I'm dwelling on that point too much, but I think that's really cool that these animals actually have this kind of spring behavior. You can see it in their dynamics, and actually this model sort of captures a lot of that. And here's one other thing that Russ likes. I'll bring you up, and it's pretty cool too. If you think about, this is sort of a tangent, but you think about how birds like sit on perches forever, right? I mean, it seems like that'd be tiring to go like hang there forever just squeezing, right? But they actually have tendons too, such that when they sit on the perch and their weight sort of squishes their legs down, it actually will clamp their talons in and let them hold on. So that's sort of cool too, that these animals have all these sort of interesting sort of like passive structures and springs and stuff like that that help them do all these kind of things. And so it's not just like, it's not like the, just use your muscles and just dominate all these kind of things. There's a lot of sort of passive structures that capture, like do a lot of this sort of for free. So hopefully you all think that's awesome. All right, so getting back to the system. Looking at this, at this model again. You see where I put my chalk? All right. So going back to the slip system. Let's see. All right. Again, the state space here. That's still dark in here. All right. All right. Oh. So going back to the system, again we have r theta, r dot, theta dot, and in the aerial phase, x, y, x dot, y dot. All right, I'll bring this one back down. And let me put in the assumptions really clearly of what this model is going to have. So the assumptions for the slip model. So one is that you have a massless, wow, that's terrible, massless leg and toe. All right, so all your mass is concentrated in that point mass that you're at the body. All right, you have an ideal lossless spring. In your leg. And that means that effectively your collisions with the ground, unlike all the walking models, are perfectly elastic. All right. Now you can see that that's not like an extra assumption that is derived from these. When it hits, even though like this toe, like sticks in right away, and kind of an inelastic collision with that toe, because there's no mass there, there's no energy, there's no momentum in it. Sorry. You don't lose any energy, and so it's actually conservative as it runs through. And then if flying through the air, there's no drag or anything, it's conservative when it flies through the air as well. And so this system actually is completely conservative in its full operation. So it's very different than a rimless wheel. And also then the other assumption we have to make is that the leg instantly goes to like the desired theta and rest length. So again, when it's massless, the rest length, it'll do that automatically, but you have to assume that you can sort of teleport it to that theta, so you don't worry about collisions with the ground or everything like that. Your leg just goes to the theta of touchdown. So the moment you take off, it's in this new configuration. All right. So now what we have to do is, now that we have the system in the model, we want to pick our surface of section. Because our goal here sort of is to turn this into a 1D iterated map, right? So that's sort of what this is all about. We're going to try to figure out how do we pick a spot. We can just look at one section and describe all the dynamics, just being like, okay, we're here, simulate, to the next one, and then we can just sort of iterate this map and figure out the fixed points, figure out a lot of things, as we did with the rimless wheel. So does anyone have an idea of what a good surface of section would be? No? What sort of like special configurations are there that we could look at?
Take off.
Take off. What else? That's one.
Full compression
Full
or rest length?
At the rest length, that's true. Full compression you could do, but that would be like there'd be a 0 R dot or something like that. But yeah, no, I mean you could. There's a lot of these sort of special configurations. But the one that you really want to look at, the one that sort of collapses things down the most, is if you look at the apex. So you look at sort of the maximum height of this flight, right? So then we can just look at that y. And the reason we can do this, I mean, describe right here. So we look in the flight phase. Now, first of all, x. We don't really care about what x is for the stability, right? It doesn't matter where it is along that position. That doesn't affect the dynamics directly. So we sort of don't care about x. So y we definitely do care about. This matters. X dot. Well, x dot, because we know it's conservative, and we know that since it's the apex, y dot equals 0, then x dot is purely a function of y, right? We can look at the total energy of the system, which is 1/2 m v squared plus mgy, right? We know y dot is 0, so that means that v is just x dot. And so you can write x dot is a function of y. All right? And so here, We know this is 0. We don't care about this. This one we can find directly from y. And so everything that happens between one apex and another apex, we know if we just know y. You see that? Yes?
We're always adjusting the angle of the spring at landing so that it is vertical at the minimum.
It's set at whatever desired angle we're at. So there's some nominal angle we want on this touchdown. So let's say it's 30 degrees or whatever. And so that means that you take off and your leg goes to 30 degrees and then you hit there. And so the touchdown angle is always the same, right? And so there's no control on this at the moment, right? It's just the passive stability of this bouncing system. Does that make sense to everyone, how we can collapse all these things? All right. Yeah.
Why don't you care about x again?
Because that doesn't affect the stability of the system, right? So like if we're trying to get somewhere, hit a target, yeah, then we have to look at x in our controller. But because the x doesn't figure in the dynamics anywhere, right? It doesn't matter. Because again, sorry, this is something I probably should have mentioned in the beginning. It's not going downhill or anything like that, right? So how far it goes in x doesn't matter. The dynamics are going to be the same, sort of invariant to that. That makes sense. And so because of that, I mean, x will be changing, but it won't affect sort of the next apex height because it doesn't figure into the dynamics like that. Does that make sense? All right. So we can represent the whole thing just using y. I guess that's the important thing to realize. So what do I want to erase? I'll erase this stuff. Throw this back up. This isn't ideal. I guess it's not going to get better than that. All right. So we go through this transition. We go from apex to apex. What we can look at is we have y apex at n. Then we need to figure out how that translates into the y x dot and y dot at that apex. All right, so we need to sort of map this one piece of information into all of these. Then we can map that into the y x dot y dot at the touchdown, so when it comes in and hits. Now we have to change our coordinate system to r theta, r dot, theta dot. This is still a touchdown. And we swing that through in the stance phase, and we get that to r theta, r dot, theta dot at takeoff. So my d and my o are as different as I can make them look. Then at takeoff again, we switch to our aerial phase. We go back to y x dot y dot at takeoff. And that brings us then to a y x dot y dot at apex. And then here, of course, we grab y n plus 1 at apex. So these transitions, I'll number them, make this a little bit clearer. It's 1, 2, 3, 4. Sorry. 7. All right. And the key now is to sort of figure out how to push our system through all these transitions so we can figure out what this mapping is going to be. So some of these are pretty easy to do, and some of them can be quite tricky to do. But all of them are quite manageable. So we can look at first is the energy, which is our kinetic plus potential. Again, is 1/2 mv squared plus mgy, right? So at the first step, if we want to take y apex and turn it into these guys, right? Again, we can have the energy of the apex, we know is 1/2 m x dot, again because we know y dot 0, plus mgy, and this is equal to a constant. And so then this means that we can say, all right, x dot equals this function of y. Right. So we can figure out what x dot is, figure out what it is, and then we know also, we know y dot equals 0. And so here then, that gets our first transition. 2 then, if you want, we know that x dot at touchdown, so this is the sort of ballistic phase coming down from apex, is equal to x dot apex, because there's no forces on it, so it's just going to keep carrying forward in x. Then we know y touchdown is going to be r naught cosine theta naught. So this is what I was talking about with there's the desired theta. Right, so your touchdown, you know you're going to touch down at this desired theta. Right? And this then, again, since we know our energy, we can get y dot touchdown. Right. So here that gets our transition from apex to touchdown. Now this is just a coordinate transformation. It's pretty easy to do too. Just make sure you get your velocities right. You have to decompose them properly. But you just transform those coordinates and you get that without too much difficulty. But then you get to the tricky one. And the tricky one, oh, great. The tricky one is the stance phase. So how do you push yourself from from when you come in and hit to squishing down and launching back out? So that's the sort of the involved part of this. So 4 is stance dynamics. All right.
Is that Y touchdown or Y cross?
Pardon?
Y limited?
Oh, yeah, this is touchdown. Sorry. So to get to 2, to get this falling phase, you know, x doesn't change. There's no forces in the x direction. Y touchdown, you fix this angle. That's the instantaneous sort of like warp of the leg. So you know when it touches down, it's going to be this high, because that's sort of when touchdown is defined, is when the toe hits the ground. And then here you know your height, you know this, and again, conservation of energy will give you this at the y dot touchdown. Right. And so that's just allows you to figure out your state when you come in. All right. So stance dynamics. So here, you sort of get an idea of what you expect the system to do. You have a spring, and if you're running in steady state, I believe you take off the same angle you come in. But so you can imagine what happens is this thing sort of swings around like this, but the center of mass, goes in and comes back out. So again, it's doing that compression and then launching itself. Right. So I think it's an assumption Raybert did for the steady state operation. It comes in out the same angle and sort of does compression in the middle. And so again, this kind of behavior is again one of those ways of defining running, like for the Groucho kind of running, is that you see the center of mass come in to the center of pressure as opposed to vaulting over it. Right. If this was a stiff leg, it would go like this, right? So that distinction is one way of defining running. All right, so we can define takeoff. So we know sort of our final condition. So takeoff happens when r equals r naught. So when you get back to your rest length, you assume that your body then goes back to the ballistic phase. And then we can write down our energies here. Now again, we're in the polar coordinates now, so our energies look a little bit different. Our kinetic energy looks like that, and our potential energy is this term, and what else do we need?
Spring potential.
Spring, yeah. So how much? It's k over 2 x, sorry, r minus r naught squared. And so using that, you probably remember Lagrange. It's not that bad in the system. You can get the equations of motion. The equation of motion here, you get and so you have all your expected terms, centrifugal terms, Coriolis terms, all that, if you try to make sense of what this is. And so if you want to get from touchdown to takeoff, you can't get a closed form solution from this. You can simulate pretty easily, obviously, but you don't get the closed form, so you can't get sort of this analytical kind of mapping. But if you use a small angle and small displacement approximation, you can linearize the system, and you can get a closed form solution for this touchdown to takeoff phase. All right? And so that sort of is the assumption that theta is much, much less than 1. Your delta R over R naught is much, much less than 1. All right. And so then you can get to a closed form solution. It's kind of ugly. It's not really ugly. I mean, it's not so ugly as to be prohibitive, but I'm not going to write it down. But that lets you actually get a closed form return map. All right. And something cool about that is that you get these two fixed points. You get one stable fixed point and one unstable fixed point. And And actually, a number of people thought that a system like this conservative system, shouldn't be able to get that sort of stability. Because if you remember in the rimless wheel, the sort of energy loss was critical towards achieving the stability. It's that when you went faster, you hit harder, you lost more energy. And when you went slower, you didn't lose as much energy, so you were able to speed up as you went down this ramp. So the fact that you can achieve stability in this system is kind of cool too, because it's completely conservative, yet somehow dynamics are able to actually sort of push it towards a repeatable state. So again, then looking at, we want to see this return map. This is from Geyer's thesis work, I believe. And it's pretty cool if I can get to it for you. All right. There we go. There we go. All right. So this is actually the return map for this sort of small angle approximation you can get analytically. And you see there's this unstable fixed point, and then down there, there's that stable fixed point. So you zoom in, and you can see sort of the stability region, that unstable one is sort of defining the boundary of the stability for that. The apex height, why does it get to that minimum there? Why doesn't it go below that 0.87? You know? Why don't we look at it below that?
That's the maximum length of the leg?
Yeah, that's your sort of height at the cosine theta length of the leg. And so you can't get below that. And then the weird thing is, and this is something I was talking about with Russ just before he went home, was why does it keep climbing like that?
Why does it keep climbing?
Well, because this is conservative, right? So how can you have an instability that pushes you up to larger and larger apex heights?
It goes into a more vertical.
At some point, though, it should cap, right? There should be another stable fixed point bouncing straight up, right? There isn't. The thing is that what we think is that unstable one right there is your vertical bouncing. And the thing is that actually, when you linearize these, they don't quite conserve energy anymore. There actually can be a non-conservative term. So I think that's what this is from. So it really shouldn't be climbing up like that. Because when you simulate these things, you don't get above that sort of second fixed point. It sort of rolls up to that, and you have this unstable one. And so then, but then looking at this again, now here's another strange thing. It looks like it should be globally stable then, right? Because if in practice we can't get above that unstable fixed point, and if you look at this, this apex axis, right, the higher it is, the slower it moves. So at your minimum sort of apex height, right, that's when you're moving fastest. It looks like it's stable throughout the entire sort of operating regime, right? The fastest it can move is that little guy on the far left, where it's apparently stable. And the slowest it can move is this vertical bouncing, is that unstable fixed point. So how do you explain that?
Seems you always learn the same angle.
That's the thing, is that that's pretty much exactly the issue, is that your failure mode can come from like coming in, squishing really low. I'm going to fall on my face here, so I should let everyone see it. You can compress and get really low, and then you bounce forward. And if you bounce forward at such a trajectory that you never get high enough for your leg to be out, touch it down, then you're just going to bounce forward, sort of land on your face, and you can't actually warp your leg. Right? Does that make sense? So that can be your failure mode. So you bounce in, you shoot across, and then if you never have an apex high enough, you'll never get your leg ahead of you. So that's the failure mode. So that's actually what we see when we simulate it. And the simulation actually looks a little bit different. There's actually, this guy looks pretty good, but if you simulate it and you have slightly different parameters, that curve there comes down a little bit lower. And so you're actually able to sort of be from the top and bounce in and overshoot and go unstable. So it's not like you're guaranteed stability by starting to bounce vertically either. So this will change with different energies, different parameter settings, and everything like that. But the take-home thing I think that's cool is that even this like sort of simplified perspective of it, you get this stability in this conservative system. You get this stability that you can see in the simulation, that even though it's not damping on any energy or anything like that, is able to bounce along and right itself. And apparently what that's related to, apparently people didn't used to think that was possible. But the coordinate transform is actually enough to get that kind of stability. Is that it's called piecewise holonomic. And by switching sort of these coordinates, you're actually able to get the sort of, that allows the dynamics to stabilize themselves apparently, as opposed to a normal holonomic system apparently couldn't actually converge in back towards this fixed point. If you think about like the pendulum on damped, something like that, that's not going to converge in, right? It has to conserve the energy. But apparently with piecewise holonomic systems, it's available. But you can read some papers and get into that. But I don't know much more than I just told you. So, all right, so here's another thing that's interesting, is that if you want to model those Raybert hoppers, right? They obviously aren't completely conservative, right? They do have some mass of the toe and in the leg. And so when they hit, they do lose some energy. Because when that toe hits and sticks to the ground, it's going to be a dissipative reaction. So you can look at this model by, I think, Tedrake and Buehler in 91. Let me use my big chalk again. And here's my old big chalk. So, looking at this. So here we have a toe mass. So we have the mass of the body and mass of the toe. All right? And this spring can possibly be nonlinear if you want. And this was largely, they did some analytics, but a lot of it was computationally driven, the analysis they did of this system. And so the thing is, because of this, this hit here, you have a loss due to the toe mass. So must add energy. And they do this with a sort of control on the spring. You can vary your spring constant like that. You can add energy to the system. And so the control on the spring is sort of their only control then. And you actually can get similar stability properties to the slip model. You can get these when you simulate it. You can find the same sort of stable fixed point, unstable fixed point kind of behavior. And so this is all what we've been talking about. Sort of the image we have is this sort of sagittal plane dynamics, right? The sagittal plane is this plane, and so this sort of idea of running through like that, right? Getting a little bit aerial phase so it'll look less ridiculous. And so the other thing, though, is that it's good for the lateral plane. If you look at this sort of lateral plane dynamics, certain animals, the same kind of slip model and that kind of behavior can actually be witnessed. So this is, again, something Bob Full spent a lot of time on. If you look at a cockroach, which has a tripod gate, here's a cockroach. I wish they actually looked like that. Probably wouldn't be as disturbing. There. And so what you have is they sort of use 3 legs at a time, and they're springy legs. As it runs, if you look at the dynamics, you actually can see you'd see that these legs are acting sort of like springs, and actually the same kind of slip behavior you'd expect you witness in the cockroaches. And so there's some cool things here. Let me show you some of these. Have any of you heard of preflex as opposed to reflex? It's sort of like pithy kind of name, I guess. So the preflex is where actually you can actually look at the time constant required for the monosynaptic reflex, which is sort of the electrical signal to go through and actually to the spinal cord and back. So not to the brain and to like the full path, but just like the sort of quick reflex kind of response. And actually, some of these creatures actually respond faster than that. So the theory is that it's actually a musculoskeletal response. Right? So it's not control at all. It's not going to the muscles or anything like that. It's tendons, it's the sort of springiness in the leg. And that is actually what's providing some of the control here and some of the stability. And so there's a really incredibly awesome video that I'm definitely going to show you regardless of how inconvenient this thing comes out.
It's not an anticipatory neural.
It's not. And that's because you can perturb them sort of almost instantaneously, right? It's like sort of slam with a perturbation, and so they can't anticipate this, right? And you actually can see like within one step, a cockroach step, they'll spring back and their center of mass trajectory will get back on track. And so it's not like they see something coming or there's like, they're going to step something that's going to hit them. It's that they're running along a perturbation and then they start bouncing right away. I'm sorry about this. I don't know what's happening here. Yeah. Now I have to
In that model, is it now the spring is actually in 3 dimensions? Is it now that you have X, Y, Z? And it's at an angle in both P and Y?
Yeah, I mean
Is that how you do that?
if you're doing the lateral plane, I think you have to have some sort of springiness like that can push you through. But you can actually look at the cockroach running along the sagittal plane, and you don't need the 3 dimension. You can you can treat several legs if they're just sort of like I think one spring in the tripod. If there's something called, I don't know if you've seen, Bob Full's work at all on sort of these templates and anchors, where the anchors are the more complicated systems and the templates are these really simplified systems. So your slip little thing here can be like a template, which is a really sort of minimalist model, but captures some of the essential dynamics and does so in a sort of concise way. And you can look at just a cockroach is following this kind of running. I mean, and it actually captures a lot of it. I mean, there's more complicated ones. If you want to look at the lateral plane dynamics, I mean, you probably need a more complicated model.
What did you say this model was called again?
This is slip. Oh, but Tedrake and Buehler came with this. So this is sort of, it has a mass of the toe. I don't know if it has a different, I don't think it has a different name. So let me get to this. There you go. All right. So first, the less exciting thing, I think, right here, but still pretty cool. So measuring the force on these cockroaches' steps, you could imagine it's difficult. Something they did actually to sort of facilitate these experiments is they actually have these guys running on Jell-O. And they can set up diffraction gratings on this Jell-O. And so you see that how it changes color when they're pushing. They're actually able to figure out the magnitude and direction of the force, to some level of accuracy by looking at that. And apparently orange Jell-O works really well. I don't know what it is about orange Jell-O, but if you ever want to analyze the forces on a cockroach's legs, start with orange Jell-O. If that's the only thing you get out of this lecture. So that's pretty cool, but that's just sort of analyzing when it's turning. They can sort of figure out, that's to look at sort of some of the springiness and the how the force response and the center mass response connect. But here, this is one of the greatest experiments of all time. All right, so this is looking at the perturbation experienced by these cockroaches. So what they did, they bolt a cannon to the back. Because pulling strings and stuff like that, it's not fast enough. It's nowhere near fast enough. This cockroach is running. Ah, oh, come on. What's going on here? All right. Really sorry. Okay. It's running. Bam. Perturbation. The little cannonball actually hits it on the way back, you see. That's not really fair. That's a double perturbation. But they track the center of mass of this guy, and actually you can see it gets back on in like less than a step. And if you look at the time scale of this and the time scale of their monosynaptic reflex, this is, it happens too quickly. And so they think it's actually compliance in the legs and everything like that that's sort of just passively tuned such that it gets banged to the side and rights itself.
Will you put this on the course website?
I think, I mean, it's Bob Full's video, but he may have it available. But a great thing is that the guy who did this thing, Devin did it, and he said, and this is like all he said, so he didn't like go through the full thing, but he's like, you'd be surprised by how little gunpowder is necessary to perturb a cockroach. And so you can only imagine the first cockroach they got out there. And they're like, ah, this is about the right amount, and just blows the cockroach up or launches it across the room. Or, so that would have been a fun trial and experiment to watch from a different room, I think. All right. Yeah, we'll watch this one more time. Yeah. I don't know. But you see, I mean, that's just a fantastic little experiment. And the perturbation, as you see, I mean, like it doesn't know that's coming. That hits it like that. It just responds almost instantaneously. So I think that's really cool. And that sort of shows this, I mean, that's slip in the lateral plane. And it sort of shows that these springs and this compliance in the actual, in the animal can actually do things that just control couldn't do. That the time scale of the response can be faster than control could achieve. I don't know if I have, yeah, I don't think I have these. So, does anyone have a question? Yeah. Okay, so that's nature sort of having this kind of spring bouncy compliance. But you can see Raybert's hoppers back in just the 80s and 90s did amazing things too. If you look at, see, where's this 1D monoped there? Some of these videos are pretty crappy, but there. So that's just a little, like a little monoped running around. You see, and it's, I mean, it's constrained to be in the plane. It's on a boom, but it could fall down forward and everything like that. It's not like it's, free to roll. So it's achieved the sort of stability bouncing around that circle. But I thought they could do more than that. If you look at, they built bipeds. This is, I think, yeah, Rust grabbed these from a VHS tape. So this is actually, what's funny is that I think this is the fastest biped around, but it wasn't quite that fast. Oh, that's sort of skipping frames. But I think it's still, unless something has changed in the last year, it runs like 2.2 meters a second. I think it's actually still the fastest biped. But I don't know, Russ would know if anything has changed.
Is it spinning around?
Pardon?
I'm sorry, it looks like it's kind of spinning around, but it's not.
Yeah, oh, but check out that. So here, oh, come on, there. So they figured they could do more. Here's a biped. So this one isn't on a boom. Bam, check that out. Let's one more time. Running there, speed, like gymnastics. That's like a robot doing a front flip. And here, this is pretty impressive too. Yeah, right over those stairs, like nobody's business, right?
If they were at a phase, whatever it is.
If what we're out of phase, if the stairs were out of phase, I don't know. I mean, you could probably imagine setting up stairs that would make it easier and stairs that would make it harder. So yeah, you probably could come up with something that would be problematic if it had to like hop. Well, maybe it could hop on one foot for a while. I don't know. It's on a boom, but yeah. So, I mean, these are I mean, even now you can look at these things, and I mean, it would be amazing if someone just achieved this, but these were back in the 80s and 90s that people did this. And so, I mean, you've probably seen Big Dog. Ray worked on Big Dog too, and it's like 20 years later than this stuff, and it's still sort of like state of the art, that kind of control, and similar control in a lot of ways. We can do some more. Oh, there's one. Let's see. And the thing is that not only do these guys do these crazy things, but their robustness is really pretty incredible. I mean, a lot of these, like the Honda robots, walk on, carefully, shows the ground and everything like that. Here, I mean, towing them along. It's probably not the most comfortable. It looks like it's a little bit less smooth, but I mean, it's running along sidewalks outside of MIT. They have, there's other ones that are just running by itself on grass and everything too. Oh, and quadrupeds are pretty cool too. That's a quadruped running down the hallway. See? And they actually did a cool paper called 4 legs running as one. 4 legs that run as one. So running with 4 legs as if it were one. There you go. That sort of use the same kind of control ideas, but actually can get these quadrupeds and actually run sort of based on the same ideas. And you see that thing's moving pretty fast and pretty robustly right down the hallway like that. So it's really pretty amazing capabilities, even today. There's one I really wish I could find for you. Yeah, and so interesting thing that some more recent work, they've, let's look at aerial. Yeah, check that out. Isn't that kind of just amazing, right? And the actuators that these guys use is hydraulics at the hips and then pneumatics along the leg. So with a pneumatic. You need that so you can rocket yourself that far. But it's just incredible. Yeah. So something that people are working on more recently is this thing called slip walkers. So you can imagine if you have like a compass gate with springy legs, right? As its spring constant gets very high, it starts behaving just like a compass gate, right? I mean, if the spring constant goes to infinity, it's rigid, it's going to be just like a compass gate, right? If you let those springs get looser and looser, it's going to start being more like one of these sort of bouncy bipeds, right? Sort of more like this kind of slip behavior. And so actually you can get stability properties. I mean, it can be stable through a relatively broad range of sort of bounciness. So that sort of the same robot can sort of, vault over its legs and walking and then start bouncing and sort of running. It actually could do that transition. And that's a cool thing also that you see. I should have brought this up at the beginning. We were talking about biology, but those transitions are interesting because if you look at the efficiency of human locomotion, so you can measure O2 consumption, and you can see sort of how efficient it is to walk at different speeds and to run at different speeds. You can look at the efficiency curve for, I believe this is like speed, and this is, let's say, efficiency. All right. And so you have something with walking, you have some curve like this. And then running, you have some curve like this. I mean, quantitatively these could be wrong, but this is a qualitative feature. So if you look at the efficiency of a person walking, and you just like put them on a treadmill and just tell them, like start walking, speed it up, and tell them just to transition to running whenever they want, they'll transition right here when it switches. And so sort of like the feeling, I'm sure, where you're like walking faster and faster, and suddenly it just feels more comfortable to just start jogging. Apparently that happens when the efficiency of that motion outweighs that of walking. Because obviously you can walk where it's uncomfortable to walk and run where it's uncomfortable to run. But the natural transition happens at that sort of efficiency. Application. Pardon? Yeah, that should be cost. Here. All right. Yeah. Now it's even more skewed. So. There we go. Thank you. Yeah, so these new sort of slip walkers, I think, hopefully you can get some of this transition, but I'm not not sure exactly where they're at now. I don't know if they have any videos of those. There's some papers about them. And I think that's all the stuff that Russ wanted me to convey. So we just have some idea of the sort of culture of these cool running models and these sort of springy things and these preflexes and stuff, and in nature the fact that springs are critical to sort of, you know, locomotion of horses and the stability of this cockroach running and everything like that. So if anyone has any questions, I'd love to answer them about anything, but yeah.
And when you were saying how they were the transitioning using the string models between walking to like running.
Oh, the slip walkers? Yeah. The slip walkers?
Yeah, the slip walkers. Is it still the completely elastic collision? Or do they actually need the
I mean,
loss of energy at that point?
I mean, I think in practice, I think they have idealized legs. I think they've done simulations with idealized legs too, but you can do either way, I'm pretty sure. I haven't looked at that work as closely as I probably should have, but yeah, I mean, for the walking kind of vaulting behavior, you need either a toe thing that's going to, or you can let your spring constant go to infinity, right? And then you'll have a rigid impact, right? So with you can treat it that way too. But then yeah, if you loosen it up, then you're not going to have the sort of intermediate, still lossy behavior. But yeah, I think they have done stuff with idealized legs and probably non-idealized ones too. So anything else?
If you get it just right, can you adjust the spring constants so that you'll get the kind of push off right before landing?
Oh, you mean like toe off kind of, or the kind of like toe off thing that pushes you forward that adds you some efficiency? Right. I think you should be, I mean, I'm not sure about how the tuning would relate to the walking things, but when you have these idealized legs with the spring, I mean, you can be more efficient than if you're vaulting over them. So I don't know if it connects to the, I mean, it seems like it could connect to that toe off kind of launch, but I'm not sure if if that is explicit, you know, just by having like your leg not, you know, be a strike with the dissipative kind of, you know, inelastic collision is going to help you. But I don't know if you get the same kind of, yeah, it seems like you should, but I don't know if that exact point, I haven't seen that exact point, but it could easily be addressed in one of their papers. I should, I don't know if I have the references right now, but I can make sure that Russ gives those to you or give those to you myself next lecture if you want to look up some of the slip walkers, because that's pretty new stuff, I think.